Hi everybody and welcome to another video of the Optimization Masterclass. So this class is going to be based on the course that I do at Imperial College, which is based on this book, Convex Optimization, of Stephen Boyd and Lieven Vandenberger. If you haven't followed the previous lectures in this series, please check the link over here. Remember that you can download the material that I use to teach the class, so the so-called smart handouts, from the link in the description down below. If you have suggestions on future topics that you would like that I cover in this masterclass, please leave it in the comments below. Thank you very much and enjoy the course. We now look at a different class of problems, the least norm problems. Okay? So we introduce this again with an application in mind. For instance, we can think about a control problem in which we have n unknown input variables, and these input variables are x1 to xn. Okay? And we have m equations of the type a times x equal to b, so linear equations, which represents m specifications or requirements in the design. Okay? So here, essentially, we want to, again, we want to satisfy these requirements. We want to satisfy them exactly. But in addition to that, we would like to produce a design which uses the least amount of energy for the input. Okay, so we have a certain constraint, essentially, that we want to satisfy. But among the possible solutions to this that satisfy the constraint, we want to find the one that, again, use the least amount of energy, which means essentially it's as close as possible to zero. Okay, so the problem mathematically can be formulated in this way, as the problem of minimizing the norm of x subject to the constraint ax equal to b. This problem is called least norm problem because we want to minimize the norm of x, and again it's another example of convex optimization problem. Again, this is not clear now, but it will be very obvious in later lectures. We have some assumptions on A. A is full rank. Again, if A is not full rank, we just discard the redundant equations and then it becomes full rank. We have to consider the fact that when m is greater than n, there is no feasible solution. This because we need to satisfy the constraint, and if we have more constraints than variables, then it means that the problem is unsolvable, is unfeasible. If m is equal to n, so if we have exactly the same amount of variables and constraints, then we know that there is a unique solution to this, and the problem wouldn't make sense because we don't have multiple solutions from which we can pick the least norm one. We just have to go with the only one that we have, and we know that the solution in that case will be A inverse times B. So the problem of least norm, the least norm problem actually makes sense only when m is smaller than n. Okay, so that we have less constraints than variables, and then that means that we have an infinite amount of solutions to the linear equality, and among the infinite amount of solutions, we want to find the one that has the least norm. Just to notice the fact that this is different from the previous problem in which here now we have m that is less than n, which is essentially different from what we had before. So, just keep this in mind. Like for the approximation problem, the least norm problem arises in a lot of different applications, not just in control. For instance, we can actually reformulate the least norm problem as a norm approximation problem. So problem 6, essentially, this problem here can be reformulated as the first problem that we have seen in this chapter. The way to do this is the following. We first compute any of the solutions of ax equal to b. We know that there are infinite amount, so we just compute one and we call it x0. Then we need to determine a matrix Z which whose columns are the basis of the null space of A. Okay, so essentially we want to find the kernel of A. What is the kernel? Well, the kernel are those vectors that multiplied by A give 0. That means that essentially a general solution, a generic solution to the equation ax equal b can be expressed as the sum of the particular solution x0 and then z times u, where u can be anything. That's because if we multiply a by x0 plus zu, then a times x0 is b, because x0 is a particular solution. And then a times z times u is going to be 0, because z, the columns of z are in the kernel of a, and so by definition that gives you 0. This, it's useful because it gives us essentially a parameterization of the solution of the linear system, and that means that we can then replace that parameterization in the minimization problem, and essentially we got rid of the constraint, and now this is just a minimization of the norm of x0 plus zu, which is nothing else than the norm approximation problem that we discussed above. There can be also an estimation interpretation of the problem. So we have consider a vector x of parameters that we want to estimate. And let's assume that we make some measurements of an underlying device, and these measurements this time are noise-free. There is no noise, so the measurements are exact, but we don't have enough measurements to actually estimate x completely. So we know that for these m measurements, we have the relation that ax is equal to b, okay? But and this will determine partly x, but since we don't have enough measurements, then x is not fully determined. Now let's assume that in our problem we have knowledge that our x is more likely to be small than large, okay? You know, another way to look at the problem is that we can say that the most plausible x is small x. And that means that, okay, we want to satisfy the constraint ax equal to b, and we also want to minimize the norm. Another application in which the least norm problem arises is in a geometric, we can give a geometric interpretation to the problem. We can consider that we have a feasibility set, so we want to find an x that satisfies the constraint. And there are, as we said, there are a lot of different x that satisfy the constraint. But in addition to that, we would like to find the point that is closest to 0. This is a geometric problem. Okay. Now let's make some some observation. Okay. So first of all, the most common least norm problem is the one that involves the L2 norm. Okay. So we have the minimization of the L2 norm squared of x subject to the constraint, to the linear constraint. This problem is has a unique solution. It's called the least square least norm problem, and the solution is called the least square solution of the equations ax equal to b, because among this possible solution of ax equal to b, we look for the ones that has the least norm. This is again a rare case of a problem which we can solve exactly, and usually, the point here is that we can always solve L2 norm problems. Okay, so these are the rare cases in which we can actually solve it, and of course they're not really interesting for our course. But there are things that probably you have seen in other courses, so it's always good to have a look at it. So we said that we can solve this problem exactly. How do we do that? Well, the first step is to form the Lagrangian. So we form the Lagrangian, which is given over here, and then we want to compute the gradient, essentially, of the Lagrangian with respect to x and with respect to the dual variable nu. Okay. So you have these two equations, and now it's just a matter of solving them, and it's just algebra, and you find the optimal solution. As for the norm approximation problem, the least norm problem can be formulated with different norms, and more in general with a penalty function. And the same consideration that the same observations that we made for the approximation problem holds also for the least norm problem. Okay, so depending on the penalty function, you get different properties of the solution, and for instance an L1 norm tends to produce a sparse solution. Okay, so a solution in which there are a lot of zeros. Keep in mind that, I mean, when we say that the L1 norm produces a solution that is sparse, doesn't necessarily mean that it provides the sparsest solution. Okay, so we know that we are solving a problem in this case in which we have ax equal to b and the number of constraints is m. That means essentially that there are solutions in which only m components of x are non-zero and the other ones are zero. So the L1 norm will produce solutions with a high number of zeros in the components of x, but it doesn't necessarily produce a solution which has exactly m non-zero components. To do that, you have to formulate a combinatorial problem in which essentially you look for all the solutions. You have to compute all the solutions to the problem the problem ax equal to b, which have exactly m non-zero solutions. Then you have to look for the one with the least norm. This is a computational problem that essentially is unsolvable for big problems, and the L1 norm is essentially a heuristic to find a sparse solution in this case.